My name is Suman Karumuri. Today I'm going to talk about taming spiky log volumes and maintaining real-time logs using Kaldb. So let's get started. So first, a little bit about me. My name is Suman Karumuri. I'm a principal engineer at Airbnb, and I work on observability. So I have expertise in log search. I've done log search systems before. I've run large-scale Elasticsearch systems before, and I've replaced Elasticsearch once at Twitter using a system called Loglens, and now again at Slack using Kaldb. I've also done quite a bit of tracing work. I was the tech lead for the Zipkin project while I was working for Twitter, and I've done end-to-end tracing at Pinterest and Slack, and I'm also one of the authors of the Open Tracing Spec. So in general, I love building large-scale observability systems, and I love building large-scale distributed systems. So that's like the logo wall of all the places I was at some point. First, let's just do a little bit of quiz just to gauge the room. So my first question is, how many of you deal with log search day to day? Like either you use it or you have to operate it or own it. Okay, cool. That's about I think half the room. How many of you use Elasticsearch or OpenSearch? Okay, that's still a good number. All right, so if you don't get any Elasticsearch references or anything, please feel free to ask. How many of you think that your logs are delayed? Okay, and how frequently do you see this problem? All the time? Okay. So, all right. So, let's jump into this. So, we also see this problem all the time. This is one of the reasons I gave this talk. This is something observability teams and engineers need to deal with every day, but doesn't get talked enough. So, for people who are new to the subject of log search a little bit, here is a very quick 2-slide primer on log search. So, logs are nothing but your printf or log.info messages in your application. And logs are widely used to understand and monitor your systems. Centralized log search aggregates all these logs across all your machines, across all your services into a central location. And then it gives you a few benefits when you do that. The first benefit you get is you get guaranteed retention. So that is independent of the life cycle of the service or machine you are dealing with. Also, having all the logs from multiple services in the same place helps you triage issues across services and machines much faster. And also, by having a consistent query and visualization experience, having centralized log search provides you a single place to access all your logs in a consistent way. A typical log ingestion pipeline looks something like this. There's an application that is producing the logs to a buffer, often Kafka. Then there's an ingester which is consuming these logs from this buffer, like Logstash. And the ingester ingests these logs into a storage engine, typically Elasticsearch or OpenSearch. And then you have a client which is accessing these logs via UI, usually Kibana, right? And so let's see what spiky logs are in this pipeline. So a log spike is nothing but you see generally 10 times more log volume than what your system is provisioned for. So for example, in the graph here, you can see the red line, which actually shows you the provisioned capacity of the cluster, any storage cluster. And then the blue line is the capacity, the volume of the logs coming in. A log spike here is an order of magnitude more logs that you see than normal. So why do we care when we see a log spike, right? So the reason log spikes are a problem is when log spikes happen, your storage is catching up, ingesting those logs, and it leads to lag. So you lag often by anywhere between several minutes to several hours. We have seen lags that are over a day sometimes. And when this happens, you lose real-time visibility into your systems. So let's say you have a major incident, and then something happened, and then from your logs, you knew what the problem was. But because of the let's say now you figured out what the problem is, you went and fixed the system, right? But because of the lags, you don't know if your fix worked because the system is actually ingesting the older logs. So you have to wait until the logs catch up. This is the biggest problem when we lose these. This is the big problem because you lose real-time visibility into your system. It's like driving a car and your speedometer is actually showing your speed from like a few minutes ago. So you're bound to make mistakes and you don't know what's going on, right? So typically for a log set system, there are 3 kinds of SLAs. The first one is actually that people usually measure is the uptime SLA for a log storage system, which actually measures how long this storage system is up. Usually these numbers are somewhere in the 90s and it's all good, right? Not really. The real SLA for a log pipeline should actually be around the freshness of data. For example, at Slack, we measured how often our lags were older than, took longer than 5 minutes to query. The first time we set up this SLA, we were very surprised because our SLA was somewhere in the 50s to 70s, and we didn't expect that. But the worst outcome was actually the perceived SLA of the freshness for logs from our engineers. They thought our logs were never fresh. And we were surprised by that. So our SLA says, hey, like it's 50 to 70% of the time we are fresh. But when you go ask our engineers, they always say their logs were not fresh. And we dug into to find out what was going on. And here is what we found out. What was happening was during an incident, you would get a log spike, and the log spike would basically cause logs to lag. And as a result, every time there was an incident, there were no fresh logs for our users or engineers to query. So every time an incident happens also coincided with the log spike, and that's the time when you needed your logs the most, and they were not available. And as a result, most people just thought we did not have fresh logs. So the perceived SLA problem is the actual SLA for your system in the real sense of the word. So this is how, so the other thing kind of takeaway from this talk is you know now how to game like the SLAs of log set systems. So these log spikes, while they violate SLAs, they cause bigger problems. It increases operational overhead for your observability teams. And usually the only way out of getting out of these log spikes is to actually peak provision your storage, and that results in higher infrastructure costs. And generally, log search is already one of the most expensive component in your infrastructure, and just throwing more money into that system just is very hard to justify. So let's see what causes log spikes, right? The most common reason log spikes happen is a misbehaving application. It could be anything from an engineer logging a log message in a tight loop. You have a loop, and then somebody is just printing a log message for every iteration to that loop. That would cause the log volume to blow up very easily if the number of iterations is too high. The other use case where you would actually see log spikes is when you have large-scale failures of key downstream applications. For example, at Slack and Airbnb, most of our applications talk to a MySQL database. So if the MySQL database is down, pretty much every single MySQL service notices issues, and it logs 1 to 2 order of magnitude more errors than usual. So this leads to log spikes. A third common reason for log spikes is the application itself got an unusual or unexpected amount of request volume, which it didn't see before. These 3 reasons are typically the reasons why you'll see log spikes from an application. There are other reasons log spikes happen from other parts of your ingestion pipeline. For example, let's take a buffer like Kafka. So in a buffer like Kafka, there could be 2 kinds of failures. It could be a production side failure, or you could see a consumption side failure. For example, if you have trouble producing logs to Kafka, one of the things that might happen is the application holds on to the logs in memory until the issue recovers. Once that happens, once the production side issue is resolved, it'll flush all those logs down to the storage, which looks like a log spike. Similarly, you can have consumption issues. When you have consumption issues, the buffer backs up in Kafka. You have a lot more logs. And when the consumption issue is resolved, all of these logs are accessed at once, which to storage looks like a log spike. You can have other parts of your pipeline fail as well, like an ingester. For example, let's say an ingester is down for a given period of time, and it comes back up. There is a backup of messages, and the ingester tries to catch up. This causes a log spike. Or your log ingestion in the ingester could be lumpy. For example, we have seen engineers log super large messages, sometimes as big as like 50 megabytes. Or sometimes people have overly complex filtering rules and things like that on specific fields in the ingester. When this happens, the ingester actually spends a lot of time parsing through messages. For example, we have seen fields where the developer is just logging one of the fields customer gave them, but the customer put in like a few megabytes of data in it, and that field made it to the logs, and then in the log ingestion, the regular expression parser was just like parsing 50 or like a couple of megabytes of messages and was slowing down ingestion, and this caused log ingestion to be lumpy. So when it's lumpy, you're stopping all the processing of logs, which causes backup, which when resolved, again, causes a log spike, right? Or it could be a simple misconfiguration that could cause a log spike. For example, you might misconfigure the Kafka consumer on your log stash, and that could lead to a consumer, a repeated ongoing consumer rebalance issue, which stops all consumption, which causes backup, which in turn, when resolved, causes a log spike because the system is trying to catch up. Or it could not be the fault of the ingester system at all. It could be that the storage, downstream storage, which is indexing these logs, has a problem and is down. So the ingester just backed up, and when the storage came back up, it's trying to catch up, right? This is another reason you'd see issues with log storage. Similarly, while we are on the topic of failures, storage can also fail. Storage, when it fails, causes backup, and when the storage comes back up, it tries to catch up, which to storage looks like a log spike, right? You can imagine any number of ways storage can fail. It could be a simple node failure, it could be a reliability or a performance issue with your storage infrastructure, or it could be something data related. For example, when Elasticsearch gets logs where one person wrote an account ID as a string and another person wrote an account ID as an int, it basically does field conflict resolution, and if the types conflict, it drops one of the logs. When things like this happen, this has a drop in throughput of ingestion, which either when it's catching up looks like a spike. So what do we do about these log spikes in this system? How do we handle them? Let's look at the application side. On the application level, things like logging in a tight loop or logging large messages are best caught during code review time. Here is a snippet of code where you are iterating over a large value and logging a large field, and you can identify these patterns in your code and catch them and fix them during code review time. If your code already made it to production and you have like log spike issues, it's not a bad idea to do code audit of critical paths to see if there are places where you're logging logs in a critical path and if you can like reduce those logs. So this is like in the application code review time. You can also actually do things that are more infra or log library level. For example, if your application is producing an unexpected log volume from application, for example, in case of a database failure, every single call is actually causing a lot of database error logs, right? A simple thing you could do in the log reporter, which is like a thing that actually takes the log from your code and then actually sends it to a file or sends it to a backend. It's called a log reporter. In the log reporter, you can apply a rate limit. And when you apply a rate limit in the log reporter, you can limit the number of times these rate limits, the number of logs your application is producing. If you have trouble with large log messages or large field types, we recommend using size limits, limiting the number of log messages or limiting the size of log messages. And a sweet spot we found is somewhere around a kilobyte for info style messages to maybe a 10 kilobyte size for errors, because you have if you have ginormous stack traces. And also, if you see people logging large fields, you can set a limit on the field size. Typically, we set it at 1K or 2K. And if the application goes over that limit, you can automatically truncate that field in your logging library. This also protects the downstream systems. And as we have seen, in case of failures, if your application is buffering the logs, you can smooth the log reporting a little bit by actually batching all the writes instead of pushing all the logs at once. We recommend small batches, reporting the logs in small batches, and limiting the number of logs limiting the number of batches you write at any time. If you're dealing with Kafka, don't write any message over a megabyte. It causes all sorts of issues. So how do you deal with log spikes at the application level? Are there other techniques? Yes. So you can sample the logs. So at Slack, what we did is we updated our logging library where every log.info location actually takes a sampling rate as input. This helps us in reducing the volume of logs, and also kind of tells the developers, gives an option to the developer to tell roughly how important this log is. So we have used this very effectively for especially noisy logs. For example, if you had this feature in your logging library, just setting the sampling rate to 5% for all log.info locations in your database library is a very good way to kind of limit the number of database error being reported over and over again in a second. The other things you could do in the logging library are you can actually prioritize log messages and only ingest the interesting logs. But be careful with this, because one man's trash is another man's treasure. So you might be dropping logs that somebody might think are valuable. So you can, again, deal with log spikes at the buffer level. Again, standard things like applying rate limits. You can apply rate limits per stream, apply message site limits per stream. You can limit the number of messages ingested per second in Kafka, right? But the biggest thing with keeping the buffer stable is actually running Kafka very well. So you need to manage these buffers well, and that's not easy. So what we actually did, actually me, is I started a new project called Open Runbook, where we are actually collecting all the production runbooks from various open source systems, from various companies, and then we are putting them in open source. The reason we are doing this is what I have seen is as I move from company to company, I was rewriting the same runbook from scratch, and most of the time I was relearning the same lessons in my runbook that I already knew before. By starting this project, my hope is we can all, basically, the collective knowledge we have gained running these applications, if we can put them in an open source runbook, we can also all share our operational knowledge this way. The Kafka runbook from Slack is already here in the Open Runbook project in that link. Please feel free to use it. And also, if possible, please contribute your runbooks to this project. So coming back, so there are other things you could do to deal with log spikes at the ingester level. For example, you can limit the number of messages going in or out of the system. You can set some limits on Logstash that limits how many messages you're consuming and how many messages you're writing. This will stabilize the ingester pipeline quite a bit. Then you can set quotas per service. For example, you can say, hey, this service gets X amount of resources, and this other service gets Y amount of resources. This helps you deal with noisy neighbors and prevents one application from hogging all the storage resources. Further, a good practice is to actually have separate streams or Kafka topics for each of your application. This way, if one of the topics or one of the application is having issues, you won't, the log ingester would not have any issues. For example, if you write the logs from two applications to the same Kafka topic, that could be a place where the log ingestion could be lumpy, because you might be processing logs from one application and then the logs from the other application are not getting processed or they're behind or something like that. But by using separate streams, you can, to a great extent, eliminate these problems. Finally, on the ingester level, you can apply sampling techniques. You can sample the logs that are coming through the ingestion pipeline. And in our experience, we recommend uniform sampling of these log messages. And the reason uniform sampling is a good strategy is if you're running dashboards and alerts off of this data, uniform sampling shows the trend information correctly. If you use some fancy sampling, it'll work, but your dashboards and alerts, when the sampling is applied, would look weird, and they may not give you the signal you think you're getting. And if push comes to shove, and if the lag is very high, in our case, if it's like over 12 hours or 24 hours to catch up or something, you can just declare log bankruptcy and say, hey, you know what, we'll just drop these logs, we'll start fresh, and there'll be a gap in the data. But remember that log sampling or dropping logs, you risk data loss, and you may not be getting all the logs that you want, and these gaps may or may not be desirable. Finally, let's see how we can deal with log spikes on the storage layer in the existing systems. You can apply, again, like rate limits. You can limit the messages written per second. You can have also limit the number of messages based on your I/O capacity. That way, you are not overwhelming you're not surpassing your disk I/O. The other thing that actually slows down reads on that slows down writes on the storage are excessive reads. A good way to protect excessive reads from happening on your system is to apply strict timeouts to all your queries, and also to limit the number of parallel queries that can run at the same time. So on the storage side, you can apply same isolation and quotas that you apply elsewhere in your pipeline. You can have a separate cluster for your large tenants. This way, the small tenants and large tenants would usually have different performance usage characteristics, and it actually works very well. And then we also, if you're using a multi-tenant cluster, we recommend using separate indices or separate tables for each tenant. Finally, we also recommend using quotas in storage as well to enforce how much resources of a cluster someone is consuming. So let's say we do all of these things, and you still cause log spikes, right? So how do you detect who is causing this, and how do you stop them? So here is a simple technique we use to root cause log spike. But we do that by querying storage. The simple query we run is we have a group of fields that we kind of know are trouble, and then we basically count the number of messages by that field, and we pick the top 10, and then we plot a chart over like the last 10 minutes, and usually there normally shows up in there. And this technique can also be applied in the ingester in a stream processing fashion, but it generally is less flexible. Querying storage, we found, is the most reliable way to detect log spikes. Finally, let me summarize this part of the talk. So a log spike is a 10x increase in the volume of logs than your provision capacity. Log spikes lead to lag, and you lose real-time visibility into your system. Application issues or ingestion pipeline issues often lead to log spikes, right? And you can mostly manage them by applying appropriate rate limits, by managing your components better, by sampling and quotas. And finally, all of these are prevention techniques. And if if a log spike happens, it still results in data loss or lag, and it leads to toil, right? So, and when that happens, typically our approach is just throw humans at the problem, right? So we paid someone, they'll hopefully do something about it, right? But if you go back to the log spike is actually, the problem with log spike is the storage cannot scale with the volume of logs, right? So how can we adapt? What if we can adapt the storage to handle log spikes? Wouldn't this problem be solved easily, right? And that's what we tried to do with Kaldb. So what is Kaldb? Kaldb is the only Lucene-based cloud-native observability database for logs. And it has low operational overhead. It runs on Kubernetes. And best of all, it's open source. It is a drop-in replacement for OpenSearch. It implements the same query API. And it is designed to handle petabyte scale workloads. It also handles field conflicts and automatically. And it is faster and could be up to 10 times cheaper than OpenSearch, depending on the configuration. So that's like a high-level overview of Kafka. So let's get into the architecture a little bit. So Kaldb employs a cloud-native architecture. Here are the components of a typical log ingestion pipeline with the Kaldb components in blue. So there is an application that is producing the logs to a collector, which writes those logs to Kafka, right? From here on, Kaldb takes over. It has a preprocessor, which takes these logs and formats them for indexing. And then, in addition, the preprocessor also enforces quotas, and it actually routes the logs to a specific Kafka partition. So the indexer consumes the messages from a specific Kafka partition, and it ingests the data and then indexes them in Lucene. And the indexer periodically snapshots this data into a deep store like S3, and it also serves queries on this data in real time. The cache component downloads the segments uploaded by the indexer from S3 and serves queries against them. The query layer handles all the incoming client queries, performs a scatter-gather aggregation across the indexer and the cache nodes, and returns the results. The cluster manager is the brain of the system. It actually coordinates all the operations across all the components. It uses Zookeeper as a persistent metadata store and also as a notification store. It deals with snapshot management, where if an indexer uploads a segment, it assigns it to a cache. It also manages lifecycle of data. So if some piece of data is outside its retention window, it evicts that data from the cache and then deletes that data from S3. It also is responsible for node management. As nodes come and go, the cluster manager makes sure that all the nodes have some task to do. So in summary, Kaldb employs a disaggregated storage architecture, and you get a few benefits from this architecture. There is a clear separation of storage from compute with this architecture. The other important benefit from this architecture is you separate the durability of the data from the storage. What does that mean? In Kaldb, the durability of unindexed data is maintained by Kafka, and the durability of indexed data is maintained by S3. Kaldb itself, unlike a typical database, is in theory not responsible for ensuring the durability of data. And Kaldb is horizontally scalable, and the Kaldb is designed so that there is minimal dependency between components. As the systems scale, usually they become all the components become tightly coupled, and a failure in any one component kind of takes the entire system down. So Kaldb is designed so to have minimal dependency among components. For example, if the cluster manager goes down, the reads and writes are not affected, which is not the case with, like, let's say something like Elasticsearch or Kafka. And so while we're looking at all of these in the context of log spikes, right? So let me get to it. So let's see how we can keep these logs real time with Kaldb, right? So let me just revisit what a log spike is. Log spike is a 10x log volume. Storage sees 10 times more logs than usual provision capacity, correct? So to ingest these logs during a log spike in real time, there is no other solution other than scaling up the clusters or scaling up the storage, right? But there is only fixed capacity, and scaling up storage takes time. So what Kaldb does, or what any system can do at this point, is when you have a log spike, the best thing you could do is you can prioritize indexing fresh data over older data. The reason for that is, let's say you have a log spike, you already know what the issue is. So what you need to know is you fix the issue, and you want to know whether the fresh logs, from the fresh logs you'll know whether you fix the issue or not. And by prioritizing indexing fresh data over older data, Kaldb can actually provide you, or any system for that matter, can provide you real-time visibility into your system. So actually, like a short quiz question. So let's say you have a log spike, and you are using Elasticsearch or OpenSearch. Does anyone know what happens when you add more nodes to Elasticsearch during like a log spike? What happens when you add more capacity to Elasticsearch? Like, what's the first thing it does? Does anyone know? Yes, exactly. The first thing Elasticsearch does when you are in a log spike is it actually rebalances the logs. So it takes the existing data and moves it into the new system. But that is exactly the opposite thing you want to do, because it's the worst decision for your logs, because not only is the new capacity not being used to ingest the peak, you're actually draining the existing capacity of the cluster to actually move the data to the new nodes. So by adding nodes to Elasticsearch, you reduce the aggregate ingestion throughput of the cluster during a log spike. So let's see what Kaldb does, right? We said in Kaldb, we prioritize indexing fresh logs over older logs. Let's see how this works. So as we have seen, indexer indexes the data into a Lucene indexer. It periodically snapshots the data into a deep store like S3, and it serves queries on that data, right? So if you squint a little bit, you'll realize that indexer is actually using Kafka partition as a write-ahead log. So here in this image, you can see that the Kafka partition has 10 messages, and the indexer is indexing the first message, right? Let's say something goes wrong, and the indexer goes boom, right? Now, a new indexer comes up because we're running on Kubernetes. Kubernetes brings up a new indexer. And by the time the new indexer comes up, there are now 100 messages in the Kafka cluster. The new indexer, for the new indexer, it's backed up. It cannot catch up. So what is it going to do? It realizes it's behind, step one. Then it actually creates what is called a recovery task. What does the recovery task do? It says, the new indexer says, hey, I'm going to index from offset 100, okay? And it's somebody else's job, not mine, to index from messages 1 through 99, right? And that's basically a recovery task. And what happens to this recovery task? The cluster manager spins up a recovery task indexer, which indexes from offset 1 through 99, and then it indexes that data. The recovery indexer uploads that segment to S3, and then it just goes away. So this is how the recovery indexer actually adds elastic I/O when you actually need it. The advantage of the recovery indexer is, instead of peak provisioning your cluster for all the time, you're only adding capacity as needed and taking it away. We actually automated this. The way we did that is we actually wrote a auto-scaling group in Kubernetes, pod scaling group, on the recovery indexer. We just always run one recovery indexer, and then there is a pod scaling group which basically scales up as the recovery indexer uses more CPU. And then as and Kubernetes, as one recovery indexer comes up, then the pod scaling group brings up an additional one. And then once that one fills up, the pod autoscaler keeps bringing up more nodes, and we'll catch up. Once all the catch-up work is done, the recovery indexers have no work to do, so the CPU goes idle, and the pod autoscaler basically scales them down, and that's how this whole system works. And this is a good way to actually catch up when you're behind. So for anyone familiar with data systems, this is nothing but a simple backfill, right? And we also seen dealing with noisy neighbors is a problem in Elasticsearch that could cause log spikes, right? So we have recommended 2 techniques of isolation where you separate clusters for large tenants and separate indexes for each tenant. And we have also recommended quotas, right? Enforcing quotas in ELK is a little bit hard because it kind of doesn't have an inherent notion of a quota. But so what we ended up doing at Slack and to some extent at Airbnb is we just set up multiple clusters. At Slack, we run over 100 plus ES clusters just for logs. And this managing these 100 plus clusters becomes very tedious and error prone very quickly. So what do? So this is the other reason we built Kaldb, because most of our work was going into operations. We wanted to automate this with Kaldb. One of the features in Kaldb is to enable this, we added a feature called multi-tenancy. What does multi-tenancy do? You can actually create multiple indexes in Elasticsearch itself for each tenant, right? And you can use it. That's not the problem. The problem is these indexes do not get any resource isolation. So if you get a query for one index, and that query is consuming all the resources, the other indices on the same node suffer in Elasticsearch. So we wanted to provide true resource isolation for these use cases. So let's see how Kaldb can isolate workloads without actually running separate clusters. Let's say you have 2 applications, right? A yellow application and an orange application. So the preprocessor sees these yellow logs and orange logs and writes them to as follows. It writes the yellow logs to Kafka partition 1, and it writes the orange logs to Kafka partition 2. The indexer, because it ties to a specific partition, indexes the yellow logs in indexer 1, and the orange logs go to indexer 2. All the queries for yellow logs go to indexer 1, and all the queries for orange logs go to indexer 2. Because each of these indexers are independent Kubernetes containers, you get true resource isolation and you get true workload isolation by implementing multi-tenancy this way, as opposed to other techniques. And this basically is how multi-tenancy is done. And yeah, let me quickly conclude, summarize and conclude the talk. So as we've seen, again, for the 100th time, log spike is a 10x increase in the volume of logs compared to the provision capacity in your system. Log spikes lead to lag, because of which you lose real-time visibility into your systems. Application failures or issues in log ingestion can cause log spikes. And you can minimize or manage these by using better management or rate limiting, better management, applying techniques like sampling, rate limiting, and quotas. And these are all preventative techniques. And when the actual, if you have a bigger spike despite all these preventions, it either leads to toil or you have data loss or lag. So we have built Kaldb. Kaldb is an open source petabyte scale Lucene-based log search engine. It has a built-in backfill operation that prioritizes ingesting fresh logs over older logs. And Kaldb features like multi-tenancy, automatic field conflict resolution, simplify log pipeline maintenance, which typically lead to log spikes. And thank you for attending my talk. And you can find me on LinkedIn or on Twitter. And here are the links for Kaldb and Open Runbook projects that I've mentioned. And some disclaimers because I work for a company. Thank you.